if you can, please send, let me know. And I will share the screen. Please let me know if you can hear me.
Yes, no problem.
Great, thank you. Again, we'll wait until the quarter past, but if there's any questions regarding the previous lectures or so, happy to start discussing them here, if there is anything.
Hi, I have a very general and
yes,
sort of unrelated question. So
that's fine too.
Yeah, thank you. So I was like watching a video about Unity and game engines, and one thing came to my mind that, of course, these are also rendering the scene to show us while we are like editing a scene. And the thing is, like when we move objects, it instantly renders the new scene, and like we can see the movement. But in my renderer, a scene like takes maybe around 30 seconds to render. So I was thinking like how these game engines work, that when you're editing the scene, you can instantly see the change.
When you say your renderer, you mean your ray tracer that you've developed in this course?
Yes, my ray tracer, yeah.
Yes, so, well, okay. So first of all, they're not using ray tracing. Some do already, but mostly the games are using rasterization in hardware, which has been optimized for 20, 30 years and more. And these games have been optimized for the rasterization engines that are available today. One of the key elements probably that takes a long time in your ray tracer is the building of the acceleration structures, I would assume. That is a part that you can accelerate greatly by using the GPU, for example, to build those acceleration structures. As well as you can run the ray tracer, you can run key parts of the ray tracing process on graphics cards today, which all the games that use ray tracing take advantage of that, as far as I know. They would be stupid not to. So there, yeah, ray tracing is just normally a software solution where all the rasterization is mostly in hardware, as I mentioned before. So there's a factor of 100 right there. And then your code is probably not nearly as optimized as game engines. They have hundreds of developers that do nothing else than really optimize the last bit of performance out of those rendering engines, these game engines. So there's no surprise there.
Thank you. And this is the same for like tools such as Blender or Unity, and these also may use rasterization?
Yes, so that depends. Blender has both a raster engine. Well, Render has a preview mode where it uses rasterization to show you the scene. It also has a game engine mode, has a special name, I forgot what that is, which is optimized for rasterization. But the core renderer in Blender is a ray tracer. And they also have a version of the ray tracer that is hardware optimized and runs on GPUs. I'm not familiar exactly how much of the hardware they're using and how much it's been optimized for GPU computing. They have a CUDA version, which is, I think, right now the only version. So it's running in software, but on the GPU. I'm not 100% sure they use the ray tracing cores, the ray tracing hardware that is on GPUs yet. It could be, but I don't know.
Thank you.
You're welcome. Happy to talk about this stuff to the degree that I know about them. Okay, good. That was nice. So yeah, let's continue. So we are still in the OpenGL part, and there's a couple of slides that are still missing. Last part we talked about the per fragment operation. Just here again the overview. Right, the most important part were the stencil test, and which is not used much, but can be very handy, and in particular the depth test, which is like used everywhere in all 3D scenes, because that's the only way you can resolve which triangle is visible if they all render to the same pixel, right? In a ray tracer, you find the first intersection, and that's clear. Then in a rasterizer, it's the depth test that determines whether you write the fragment of a triangle into the frame buffer or not, and you only write it if it is closer to the camera than anything you've written so far. Of course, you realize that right, the depth test is at the very end of the pipeline, and so you might have rendered many more triangles. You might have rasterized and shaded many more triangles that you've already written to the frame buffer, and then comes a big triangle that is in front of all the others, and it simply overwrites everything. So all the work you've spent in rasterizing all those other triangles and shading all the other triangles is essentially gone that way, right? And so optimizing this and not rendering things that you know will not be visible, or rendering actually in front to back order. So you render first the stuff that is close to the camera, and then the early depth test or the occlusion query can be used not to spend too much work on the triangles that eventually will not end up on the screen. Yeah, so we talked, the occlusion query can be used for doing some of that. We talked about blending, which is that process of mixing the color of the fragment with whatever is already in the frame buffer for semi-transparent objects like windows or glass objects or things like that. We talked about the RGB conversion and dithering, and so we're at the very end of this pipeline now. So let me just jump ahead. We talked about blending. I talked about the this part here. We talked about, oh no, this is I think where we stopped, the frame buffers. I talked about that of course there is a color buffer, often combined with an alpha channel, which stores how much of a pixel is covered, which might come either from the multi-sample part, right, where not all samples might be covered by a triangle, or it might come from the application which explicitly sets an alpha value for vertices, which then gets interpolated and rasterized. There's double buffering if you want to render things while you are displaying it without disrupting the frame buffer that you're currently displaying. And then you swap the two, and then there might be stereo for VR and other applications where you present different content for the left and the right screen. They must be aligned with each other. And so you might actually end up with 4 buffers just for color. And then, of course, there's the depth buffer, potentially a stencil buffer for doing those stencil operations, and the application can add more buffers. We talked about the stencil. Oh yeah, I already talked about this part. I now remember the cleaning, and I guess that is where we stopped, right? So yes, so the besides the frame buffer as such, there's the notion of a render buffer, which is essentially the memory for color, for stencil, and the depth buffers. And OpenGL allows you to control these explicitly. So typically for the main frame buffer, that gets allocated when you open a window in the graphical user interface, right? You specify which configuration you want for these different buffers, and so they are pre-allocated by the time you are dealing with this window in OpenGL. However, OpenGL allows you to allocate additional frame buffers and control the render buffers, so these memories for color, stencil, and depth. And so this GL render buffer essentially again allocates IDs for those buffers. You can bind them pretty much like textures or general buffers, and as we discussed before, and then you can allocate memory for those buffers once they're bound. And then in addition, so this is for the individual buffers, and then you can have a frame buffer object, and you can bind the frame buffer object. For rendering. So again, you can have multiple of those, and yeah, so the target can either be a draw buffer, a draw frame buffer, so that obviously says, okay, use this frame buffer for drawing into, and you can also, there's a different target read frame buffer that can be used, and we'll talk about to read pixels from the frame buffer, for instance, for copying it into a texture. And this default frame buffer that I just talked about, which is pre-allocated, always has the ID 0. Now, of course, once you have a frame buffer, you need to attach these draw buffers to them. And there's this GL frame buffer render buffer, funny name, where you can now attach a render buffer to those frame buffers. And you have to specify how they should be used and for what to attach them. You can, the funny thing is you can also attach a texture to a frame buffer, in which case you might actually render directly into a texture object. However, you cannot simultaneously render into a texture buffer and at the same time use the texture for rendering. At least that is undefined behavior. In some cases that actually works, and people have used this for special effects. But of course, that arbitrary things can happen, and so there are some limitations that you cannot write and read from the texture essentially at the same time. So the final, almost the final part is that other than just displaying the pixels in the frame buffer, you might actually want to read them back for printing, for storing them in a file or whatever. Or using them in a texture if you don't want to directly render into the texture, which actually wasn't possible a while ago. And so this GL read pixels, essentially you tell OpenGL that it should copy back the pixels from the currently bound frame buffer. You specify the location, the width and height, so you can read subparts of the image. And you specify, again, similar to when we talked about textures, how to load texture data into from the application into a texture object on the GPU. Here you now specify the format and the type and where to write this in the application area. And it reads from whatever internal format the frame buffer has and converts it into the format and type that the application expects, and writes it to the location that is pointed to by data. And so what essentially what's happening here is similar to what happens on the texture side. So it takes the RGBA data from the color buffer and converts it into a floating point value, at least implicitly, right? So typically you store the color as I don't know, 8-bit integers, converts it logically into a float. It clamps it to 0 and 1, which is necessary if you're using a float frame buffer, for example, or half float frame buffer. Then of course you can represent things that are outside the 0, 1 range, so that gets clamped, and then it gets packed into what the format, what the application expects in terms of the format. And also that is hardware accelerated. These kinds of operations are typically fairly expensive if you do them on the CPU. So the GPU has special code path for doing all of those conversions. Then there's a couple of special functions that are important to be aware of for OpenGL. There is glflush, which just makes sure that all previous commands that your application has issued to OpenGL actually gets written to the GPU. So the point is that because the switching from a user space application into the driver that runs in kernel mode in the operating system can be quite expensive on modern hardware. What OpenGL typically does, it buffers a number of commands and only sends them if the buffer gets full, or if you issue certain queries or certain operations which would require to read back information from the GPU, and then then implicitly OpenGL flushes the buffer and writes it to the GPU. So normally you don't have to do this by hand. But if you want to, then glflush does that. However, glflush just sends it to the GPU. It does not wait for all of the drawing to have finished. That can be done with the glfinish call, which essentially implicitly does a glflush, but it also waits until all of those operations have been completed. And that can actually take a while because the buffer can be fairly large, and there's a lot of processing, right? There could be large triangles that need to touch many, many pixels. So that can take a while until all of that has actually finished. I mean, GPUs are really fast, so take a long time is a relative thing here. It probably still runs at real time, but you can relative to the rendering speed, so the glflush and finish calls, particularly glfinish, can greatly diminish the performance of the application. You can also, so glfinish essentially does an implicit sync between the application and the GPU, so that the application now knows that whatever it's done so far actually has been executed now. You can also do this asynchronously. So glfinish is a synchronous call because that call waits until everything has finished, and only then glfinish returns. There is a different way of doing something similar, which is asynchronously. You can have this glfence sync, where you define a condition, and that condition is inserted into the command stream that is being sent to the GPU. And that condition gets signaled, or that synchronization gets signaled when the simp object essentially went through the entire pipeline. So you know that everything that you sent before that fence has now been executed. But this call doesn't wait for this. Instead, there is a separate call glclient wait, where you can specify that you want to know whether it has finished, and you can specify a timeout where, and there's slight differences between the two calls, where you can say, okay, I want to check whether it's finished, and the timeout says how long you're willing to wait for that. You can say, oh, I don't want to wait, I just want to know whether it's done now. Or you can say, okay, I'm willing to wait a millisecond or something. glhint is just a general way to give certain informations to OpenGL about how it should render things. So it's essentially tell OpenGL, okay, I don't worry that much about quality, and then maybe OpenGL can take a faster route for rendering. And then there's a number of glget calls for different state to query, to read back from OpenGL of what the current state is, and sometimes, for example, the exact number of texture slots in a shader. There's a minimum that the specification, for example, requires OpenGL drivers to offer, but any driver can offer more, and you can query how many there actually are, and similar for many other properties of OpenGL. I refer you to the documentation for more details. I briefly talked about some of the aspects on this slide here. As I said before, OpenGL does not guarantee any specific algorithm for rasterization, but there is certain freedom about how things are to be rendered, to be rasterized. There are certain rules that must be obeyed by any implementation, but certain things are not required. However, so for example, like how many bits are being used for representing the depth value, or exactly how depth is being encoded and quantized. That is typically not something that you can set exactly. You can say how many bits you want to be represented in the frame buffer, but still the GPU is free to choose exactly how it uses those bits. And so because of the quantization in the frame buffer, because that has a finite resolution, right? Different GPUs might end up rendering different triangles differently because the Z comparison just is slightly different. So if you have two intersecting triangles, the line of intersection, for example, it's not clear that this is always exactly the same pattern. And however, there's a number of invariants that OpenGL guarantees. So for example, OpenGL guarantees that it doesn't matter that if you, with the restriction that I'll just talk about in a second, if you don't, essentially the output will always be the same given the same input, unless you are switching options on and off in OpenGL. So there's this GL enable and disable call that I refer to. So for instance, you can enable Z buffering and you can enable texturing and disable texturing. And all of those calls essentially give up on guarantees. So if you render the image with Z buffering and without Z buffering, OpenGL does not guarantee that you get exactly the same pixels. However, if those options are all the same, right, and you send exactly the same input data again, then you are OpenGL does guarantee you that you do get the same the same results back. And so yeah, it's probably too detailed to go into too much detail here, but so just know OpenGL does guarantee some invariances of this sort, but it doesn't guarantee any absolute guarantees about how exactly it performs its rendering. Yes, and that's it for OpenGL so far. The next set of slides, however, do belong to OpenGL because that is where I want to talk about about shading languages, specifically the OpenGL shading language. But if there's any questions in between, feel free to ask them now. Okay, so I'll just start, but feel free to interrupt. Yeah, so already I talked about hardware briefly. I'm just talking about the GPUs or the graphics cards or early onwards were essentially just memory and a little bit of hardware to scan out the results to an analog display. Of course, these are all digital connections to display now. Here you see a little bit of different aspects of the development of GPUs, specifically with respect to their abilities to run shaders of some sort, right? Or to run certain parts of the application, of the rendering pipeline. So the pre-GPU graphics acceleration, so the Evans and Sutherland machines or silicon graphics machines, they were the first to introduce a form of GPU where they had specific chips that, for instance, performed the transformation of vertices. So this was not running a shader yet. This was just give OpenGL, you give a matrix to OpenGL, and then OpenGL or the hardware actually implements the transformation, the transformation of vertices into the model view or into the camera coordinate system, right? And at the time, this was big hardware. So here you see an image of the geometry engine of an infinite reality machine, which was actually about, right, this was an entire 19-inch rack, actually bigger than a 19-inch rack today. This card here is 50 by 50, roughly 50 by 50 centimeters. So it's a huge card here. These are ASICs that have been designed by Silicon Graphics at the time. And you could have, if I remember correctly, 2 of those geometry engines or geometry engine cards in one of the SGI machines. So they were huge. They're for storing the raster, for storing the frame buffer, there were raster manager cards. They were the same size, and you could have up to 4 of them. And so you see this adds up quickly, where the GPU really becomes more than a computer in itself. And it was only doing, right, just storing the pixels of the frame buffer. It did the rasterization, and it did the vertex transformations. All of that around 98, this got integrated into a single card that you could add to your PC. There was the NVIDIA TNT2 or the ATI range of Voodoo cards. And but they didn't even do the vertex transformation yet. The vertex transformation was still on the CPU. And there was very limited math for pixel operations that you could do actually on the GPU. So vertex transformations are essentially a step back, but now you had it on a single card that you could input into your PC. The second generation of GPUs, which was 99, 2000 timeframe, is where transform, but also lighting computations were per vertex lighting computations, which also the SGI machines could do. The other thing the SGI machines, of course, could do is texturing, which was the big thing back at the time. So that was possible also in the second generation of GPUs. It was a little bit more configurable how those operations could be done. They allowed certain limited but fixed computations to be done. It wasn't really programmable in any sense. The third generation then added vertex programmability. So you could have a vertex shader. It was very limited, so it could only have a small number of instructions in the vertex shader. And you could, again, have a fixed but more flexible set of computations on the pixel pipeline, but you couldn't program that pixel, right? There were no fragment shaders yet, but there were some fixed computations, you could say, right, similar to the blending operations that we just looked at the end of last lecture. So there were similar operations you could do to fragments after rasterization. But you could just set some parameters and either switch them on and set parameters or switch them off. And it was really the fourth generation around 2002, where now you had vertex and fragment shader operation. Again, very limited in what they could do. And actually there were different pieces of hardware. And so the capabilities of a vertex shader were actually very different than the capabilities of a fragment shader. That was then unified. So at some point we got unified shading, which the same piece of hardware actually executes both types of shaders today. Later on, the geometry shaders were added. This is where the unified shaders happened, 2007 timeframe. And then later on, 2009, 2010, right, you also added compute shaders, which are not running inside of a pipeline, or only at the beginning of the pipeline with mesh shaders, but they are a very recent addition. And also Hull and tessellation shaders were added, which essentially have become useless now, or very limited use. So, but let's look. So essentially, the hardware developed dramatically. And if you look at, we quickly talked about this in a couple of lectures ago, that essentially GPUs are now highly parallel processors with a little bit of extra hardware for doing rasterization and texturing and a few other things, and of course a frame buffer. And so the notion of shading compute, of programmable shading on a GPU became really important. However, this idea of shaders is actually much older. This idea of essentially having small plugins, small program fragments that allow you to modify the rendering process were thought about much earlier. We'll talk about this a little bit more in the next slide. The problem with those shading languages is that they run essentially in the innermost loop of your renderer, right? For every fragment that you generate, and there, of course, are millions of them, your code must be executed, so that code needs to be executed extremely efficiently. As that's both true for rasterizer, but also for ray tracer. So the shaders that people thought about earlier on, now I'm abstracting a little bit from the rasterization engine that we're currently looking at. They were first thought about in the context more of it ended up being rasterizers. It essentially was the Renderman shading language that started all of this. But if you abstractly think about that, there's this notion of, oh, what happens at a surface, right? So you have material shaders, or sometimes called surface shader, which get the incident direction, the outgoing direction, and at the location where you are on the triangle, and they determine how the light is being reflected at that point. You can also think about light shaders, which determine, given a point in the scene and given a point on the light source, how much light is emitted from that light source towards that point. Or volume shaders, which actually determine, right, for any point in the volume, how much of the light is being absorbed there and how much that point is in the volume is transparent. So we might talk about volumes a little bit later here. Displacement shaders, they essentially run on the geometry and allow to modify the triangle. Essentially, they can displace all points on a triangle. Or camera shaders that determine the rays, let's say in a ray tracing context, they determine for each pixel which rays to generate. So you can implement arbitrary lens systems, for example, not just a a perspective projection onto a planar surface. So people came up with these notions, and the mothership here, the mother of all shading languages, really is the Renderman shading language. I'll talk about this on the next slide. Today, probably the best, besides Renderman, the best implementation is actually the Open Shading Language by Larry Gritz, which is an open source project, but the problem a little bit is that, and that's important to point out here, shaders are, right, very specific for the entire rendering process. And you often don't just want a material shader, but you want a full material definition. And that involves more than just a shader. There's some slight differences here. And there are not really, despite these shading languages, there's no real good definitions of how to describe materials. There's two developments still ongoing and successful to some degree. The one is Material X, which is an open source project. And then there's the material definition pushed strongly by NVIDIA, but it also hasn't really caught on too much yet. So there's still work to be done. So let's look a little bit at the on the tradition of shading languages. I mean, as I said, the real first language was RenderMan, which was designed at Pixar in 1988. One of the key contributors was Pat Hanrahan, who is a professor at Stanford for computer graphics. I actually spent my postdoc time as a visiting assistant professor with Pat at Stanford. A really nice time. So this is still widely in use today, but mostly for offline use. That is what it's designed for, and for high quality, more ray tracing like applications. Originally, RenderMan was a raster, or actually a scanline, sort of scanline renderer. It was the it was some sort of rasterization, but in a different way than we've discussed it here. But Pat actually, there was work before that. Actually, Rob Cook, in 4 years earlier at Lucasfilm, came up with what's called shade trees. Essentially, these are individual blocks that you can connect to each other, which in a flexible way, and each of the blocks has a certain functionality, right? So you have 3 inputs, and it performs, I don't know, some function on these inputs and generates potentially some outputs. And you could configure them into kind of a network, actually very, very similar to you might know about shading networks in. We just talked about Blender before today. Blender also has these shader networks. This is where they come from. And then a year later, Ken Perlin, who you know from the Perlin noise, came up with the image synthesizer, which actually applied this in the context of deep pixels. So in that, deep pixels here were not just a frame buffer with color data and maybe depth and some other stuff, but you could store many, many more things into the frame buffer, like normal, the normal vector and texture coordinates or temperatures or any sort of other data. And then you can run the image synthesizer on that, which was much more language-like, right? You didn't have control structures in Rob Cook's shade trees, really. Now in the image synthesizer, you had control structures and things like that. Again, all of that was then picked up by Pat Hanrahan, who used a C-like language to do that with Pixar. And then for about 10 years, nothing really happened. And it was only when graphics cards became powerful and programmable enough, or it was clear that they would become programmable, when this whole topic of shading languages came up, and people thought about how to actually implement this for a GPU rasterizer. And the first work actually happened while I was still at Stanford. And I was involved in some of the first meetings, which was really an interesting joint project located at the university. But we talked to people at Sun, which played an important role back then, at Silicon Graphics, NVIDIA, ATI at the time still. And there were still many other hardware vendors for graphics, for GPUs at the time. And learning how the GPUs were supposed to develop in the coming years. And there was a lot of interest at the time in being able to program these GPUs. What came out of that was the real-time shading language, RTSL, at Stanford. I was gone by the time, which then eventually was picked up by NVIDIA, and they developed a shading language called CG that was widely used. It was actually cross-platform. And those ideas were then picked up by Microsoft. They called their shading language HLSL. And GLSL, it was picked up at Kronos for OpenGL, all in 2002. Today, the cross-platform, well, first of all, if you use OpenGL, GLSL is still the primary original shading language, of course, for OpenGL. But OpenGL can now also deal with SPIR-V shaders, which was designed for Vulkan, but it has become like the cross-platform way of specifying shader code specifically. This is not a source code language anymore, where you don't specify source code, but this is already compiled into a lower level representation, binary representation. Which helps the game and the game people, right? Because they don't need to distribute source code. But we'll talk about GLSL because that's most closely related here. Again, we have this pipeline, and you see all the parts that are programmable in bluish here, interspersed with stuff that is fixed function in OpenGL. So let's quickly look as GLSL as a programming language. It's essentially I think that was here. Sorry, I forgot to say that the syntax of GLSL is similar to C. It's built on top of C, but there has some additions. So it's, for example, it supports overloading. We'll go through some of them, is then used for the different programmable stages. So some of the differences or similarities, there's all the basic data types, float, bools, integers, also unsigned integers and things like that. But it has, for example, one difference is that it has this kind of constructor syntax where you can construct a more complex data set, like a vector, a vec3d. So vectors are first, how do you say, missing the word right now, are intrinsic types, which is not the case for C, of course. You can have vec2, 3, 4, so vectors of different numbers of elements, and you can have Boolean vectors, integers, vectors, unsigned vectors, and so on. There's matrices as basic data types as well. Square matrix, 2 by 2, 3 by 3, and so on, but you can also have rectangular matrix here, where you specify the size. There's samplers. So essentially, samplers allow you to access a texture. Again, the texture itself you handle through OpenGL, but you can, the way to use the texture is through a texture sampler, which is essentially, again, a data type in GLSL. And there's different forms of samplers in terms of what type of textures they're sampling and what they return, whether that's a float, an int, or so on, and whether that is actually a vector, right? A texture can return a color vector, for example. Yes, there's structures, just as in C. There's arrays, which, unlike C, are really full data types. C only knows pointers to the first element of an array. So here they're full data types. But there's also some additions that don't exist in C. First of all, well, const does exist in C, but it's the same here. So it's a compile time constant, and it's used and it's implemented more aggressively than in C. There is a storage qualifier in, which says this is a variable that is input to the shader. So for a vertex shader, that is, this is data that is input. So for example, the input from a vertex shader to a fragment shader is then is marked as in for the fragment shader. There's centroid in for the vertex shader, which means, oh yes, input, but please interpolate it to not to the exact sample location in the rasterizer, but to the center of the pixel, which might be different. Of course, there's out. So for the vertex shader, it says, for example, what data should be output, and of course, the output of the vertex shader needs to match the input of the fragment shader. There's a centroid in out for the same thing. There's uniform variables. Again, we talked about uniform variables already. You cannot write to them; they're read-only, and they get their values from the application that uses the shader. And there's in-out variables that are only used for function parameters, and functions are very limited in GLSL. They're not as general. And certainly, for example, you can't use them recursively. There's interpolation quantifiers that tell you how the data should be interpolated. There's flat, which means don't interpolate. Just output the data just as it is, and it will, for any primitive, it will, if I remember correctly, will take the first vertex, the data from the first vertex, then for all fragments that are generated from that primitive, for that primitive. Smooth is the prospectively correct interpolation, and non-prospective is the linear interpolation in screen space. So essentially not dividing by W as we would otherwise have to do. Yes, if you want to connect a fragment shader to a previous vertex shader, you need to make sure that the variable names and the types of the variables, of the input and output variables, that they match. You cannot pass a sampler, right? That doesn't make sense. First of all, you can't interpolate it. So samplers must be defined per shader. You cannot pass arrays except implicitly for the geometry shader. Yes, for the vertex shader, you get the arrays. Actually, I'm a little bit confused here. I think that is actually only true for geometry shaders. The vertex shader. Okay, we'll have to look at that later. Vertex shader cannot have structures, but arrays. And geometry shaders, since they receive an entire primitive with for example, 3 vertices, that it always receives arrays. You cannot interpolate int variables because that doesn't make too much sense. And fragment shaders cannot output matrix or structures because the output then goes to a frame buffer, and matrices or structures don't make much sense for frame buffers. Instead of defining the input and output variables per shader, you can actually put them into a structure, into an interface block, where you kind of can group them together, which is usually the more nice way of referring to them. And you can put such an entire block into a uniform buffer, for example. So that's also useful for that. We talked about the layout, right? So which slot a certain variable goes into. And that is something that you can also specify already in the shading language. We talked about that you can actually specify this also for OpenCL. In many cases, it's easier to just already specify this here in the shader. So here's the predefined variable. So any shader, any vertex shader in this case, always gets a GL vertex ID, which is essentially the number of the vertex in the array that was issued in the draw call. And remember, I only talked about this quickly, is there's instance calls. So you can say, for instance, you can draw an array that draws, I don't know, a chair, and you can say, oh, I want 25 instances of that call. So essentially the same draw call gets repeated 25 times. And the only difference between them is that the vertex shader gets that instance ID for each call, that the same data gets rendered again. And for instance, the vertex shader can use this instance ID to index, to use a different transformation each time, right? By placing this chair, I don't know, in a row or in some form of a 2D matrix or something. And then, so these are the predefined input variables. Of course, you can define more for all the attributes. And then the output of the vertex shader, right? Of course, you need to specify the position that OpenGL needs that. You can specify the point size. So we didn't talk about point rendering, but you can actually, OpenGL has so point is not usually is infinitely small. in OpenGL, that would make no sense. So you can specify what's the radius essentially of a point that it should render that. And you can also, I didn't actually talk about that, but OpenGL allows you to clip not just against the view frustum, but you can specify additional clip planes. And the shader can compute what is the distance of this vertex from a clip plane. So think about these distances here as the window edge coordinates that we talked about when we talked about clipping. So essentially, this says how far away is this vertex from the clip plane. This is then being used to do the clipping against the plane. So you don't specify the plane, but the distance from a plane that OpenGL doesn't need to know about. It only needs to know about the distances. But again, you can add additional variables from the vertex shader, but they have to match then the input to either the geometry shader, or if you don't use geometry shaders, the input to the fragment shaders. So geometry shaders, they get the first structure here is they get an array of input. So for each of the vertices, that is part of the primitive, and each one consists of exactly the data we just defined, but an array of this, because you get 3 for a triangle, of course. You additionally get the number of primitives that have been processed so far. So that's different from the vertex ID we had for vertex, right? Here it's the primitive ID. And then they output the same data. The geometry shader output the same data for each vertex that they output. Primitive ID and layer here is again it's clear. GL layer specifies where the data should go in the frame buffer. It's something I didn't talk about, an advanced feature here, and you can skip this here for now. And then the fragment shader, they get the fragment color, the fragment coordinates. They get, so they don't get W, but they get 1 over W. So vec4, they get a flag whether they're front facing or not. They give the clip distance point coordinates. So this is, right, again, a point can be larger than a pixel. And so you get to know where you are in that, in the local coordinate size, the local coordinate system of the point. You can use that, for instance, for shading the different samples inside a quote point, OpenGL point, the primitive ID, and you can output the fragment depth, of course, as well as color and other data. So how can you do operations in OpenGL? Obviously there are vectors are a key element because we typically operate on colors or vertices, things like vectors. These vectors actually implicitly have named components. And actually there's 3 types of names, X, Y, Z, W, of course, if you think of this vector as a point. Or you can index the same vector as RGBA if you think about the vector as a color value, as color values. You can also index them as STPQ if you think about the vector as texture coordinates, 2D, 3D, and maybe even 4D texture coordinates. And the funny thing in GLSL that's very different from C is that you can actually swizzle those values. And this is probably best explained by, and you can do that on the left-hand side and then on the right-hand side. So, right, for instance, here we create a 4 vector, 1, 2, 3, 4, and then you could create a new one and you assign to it the value of pos, but now you can specify what should be the order of that. So you take the values of pos, but you change the order. You say, I want first W, then Z, then Y, then X. And so this vector Swiss then has the value 3, 4, 2, 1 in this case, right? But you can also duplicate values, like in the third line here, where you just say, okay, I want twice X and then twice Y. Of course, the number of components that you specify here on the right-hand side needs to match the dimension of the vector on the left-hand side. Yes, you can also write to individual components here. pos.xw means leave the entire vector alone and only change xw. And again, you can specify also which values from the vector on the right-hand side should go where on the left-hand side. So you can also swizzle while assigning to a vector. All of the vector and matrix computation operate on a per element or per component size. So if you add two vectors, it adds all the elements. Same for matrices, except if you do multiplications that involve a matrix. So matrix multiply, of course, gives you what you expect, but also vector matrix multiplies are doing the correct thing from linear algebra, as you would expect. There are also some differences in control flow for the shading language. So it has all the usual control flow that you know from C or C++, so if statements, while, so and so on. It has something that's very unusual for C, and that's the discard statement, which essentially means forget about this fragment. That simply means whatever fragment you currently have, this is marked as not applicable anymore. There's no more computation happening on that fragment, and it will not be written to the frame buffer, right? The thing to keep in mind here, though, is that GPUs essentially operate on a SIMD processor. So GPUs are essentially SIMD processors, or SPIMD, which is a slight variation for that, but doesn't matter here. So SIMD is a single instruction, multiple data, which essentially means that some functional units that you saw in these SMs when I talked about the GPU a little bit back when we started with OpenGL, right? These functional units that do floating point operations, they don't individually do stuff, but they all do the same thing, and so they operate always on a vector. And now this is something that is extremely useful for graphics, right? For instance, you can do the operations for the next 16 pixels, right, or a 4x4 tile of pixels, and since they typically all run the same shader, right? You can run them all in lockstep. And so discard at first just means, oh, don't do any computations for one of the pixels here. But since, right, the program executes for all the pixels simultaneously, right, it would still continue executing, except that if you did a discard for all the pixels, right, at which point the computation stops completely. Yes, this computation on typically a tile of pixels also enables certain operations that otherwise would be very difficult to implement. So, for instance, for textures, right? Remember when we talked about textures that we might actually need the dx, so the step size in texture space between one pixel and the next one. And these kind of derivative functions would be very hard to compute if you only did the computation for a single pixel, because then you don't know what happens for the next pixel. If, however, you do the computations for a number of neighboring pixels, an entire tile, you can compute this because you do have the data for the neighboring pixel because you're computing it at the same time. And so these derivatives are actually not pointwise differences, but they are computed typically by divided differences. and OpenGL or the implementation of OpenGL typically use quads for that. So you actually do the rendering on 2x2 pixels, and the derivatives are actually taken from just taking the differences between two neighboring pixels, either in the horizontal or in the vertical direction. There's, however, these are of course approximations only to derivatives, but they are typically good enough for most of the things that you want to use them for example, for texture access. But you need to be aware of them, that there might be some artifacts depending on what you're doing with these approximate derivatives. So here, so one typical type of shader is, for instance, a Tunify shader that, right, so shades objects like you would do for cartoons. In which case you typically, right, you don't have these smooth transitions, but you only have a number of coarsely of different colors, and there's only a few of them, right? So here, for example, you get a intensity, and depending on the intensity, right, if it's almost white, then you use one color. Between 50% intensity and the first one, then you use a different color. Between 25 and 50%, yet another third color, and everything else. So instead of a smooth interpolation, you actually artificially create a quantization. In some sense, artifacts, but in this case, it is intended. And if you use techniques like that, you get characters or objects that look somewhat like you would do them for cartoons. That's a very simple version. There's much more elaborate versions of that you can think of. Of course, there's certain operations that are you don't typically do in C programs, right? So there is also special functions. There's the standard things like sine, cosine, power, min, max, clamp, and so on. Normalize, of course, is something that typically does not exist. Dot products are not available in C natively, or cross products and things like that. And then there's very shader specific calls like face forward, right? Given a normal vector and in an incoming direction, the normal here is the reference normal, and it returns either the normal, the n here, the first argument, or it returns minus n. So it orients the normals to be on the same side of the incoming direction. Or reflect, which takes a normal vector and an incident direction and reflects the incident direction at the plane that is specified with a normal vector. Or refract, which does the same thing as you would expect, given an index of refraction, a relative index of refraction between the front and the back side. Or smooth step, which does a cubic interpolation of the variable x between 0 and 1. Right, so it's a smooth transition between 0 and 1 with tangent 0 at 0 and 1. Or mix, which interpolates between x and y depending on a variable a here. This is a linear interpolation in this case, so often being used to interpolate between colors or things like that. And there's obviously also noise functions that are there built in already. There's a huge list of texture functions, too many to really talk about here. So you can directly sample the texture, just giving it the texture coordinates to a 3D or whatever. You can also do homogeneous projections. There you can do the texture access together with MIP mapping, taking MIP mapping into account. You can offset, you can have offsets into the texture coordinates. You can take the derivatives that I just talked about into account, which is important if, for instance, you want proper MIP mapping, in particular MIP mapping with anti-aliasing, with anisotropic filtering. You can also fetch textures without doing any interpolation, which sometimes you can do so you store variables in a texture, for example, and then you read out the variables. Essentially, you can think of the texture then as a large array. And you can combine many of these things with each other. I already talked about derivatives, right? That the way the SIMD computation easily allows us to do them. And so there are constructs that you don't find in any other, well, I shouldn't say any other, there probably are languages that have similar things, but here you can actually take the derivative of an arbitrary expression E here and compute the derivative of that entire expression relative to the pixel coordinates X and Y. And that's, if you think about this, that's a little bit surprising, right? Because it promises to do that on the pointwise and with respect. So it's not, right? It's typically something where you need a formal tool like Mathematica to do that for you for complex expression. However, here it turns out it's very easy to do because of that divided difference. Well, so essentially what those shaders, what these expressions are doing, they simply compute the values of that expression, right? And then when they come to the point where they take the derivative here, they simply look up the value of the expression in the neighboring horizontal or vertically neighboring pixel, and take these differences as the derivative, right? And since we're doing these computations in parallel, that's easily possible. Like you just need to look it up from the neighboring pixel. And similarly, you can, for instance, also compute the width of a triangle, which is really the sum of the absolute sizes of these derivatives. So, right, that's essentially the size of a pixel on screen in texture in terms of the expression E. So typically E is a value that is typically texture coordinates. So in this case, it's the footprint of a texel, right? If E is a texture coordinate, then F width of E is the size of the diameter of the footprint of the footprint of a pixel. And so, for instance, you can use that to filter textures. But there's many other approximations. You can use the same F width, for example, to do anti-aliasing, right? If you compute in a shader a certain function, you want to make sure that this function doesn't have too high frequencies, right? So let's say you do a noise function, right? You want to make sure that this noise function, in terms of let's use the turbulence function, right? In turbulence function, if you remember, you take octaves you add noise functions with different frequencies, double, quadruple, and so on of the frequencies. However, you want to make sure that you are not adding too high frequencies, right? Given the pixels on the screen, because if you would add too high frequencies, you would create aliasing. And so you can essentially use the F width expression here to find out how big is a pixel relative to what you're computing, and essentially stop computing the turbulence function when the frequency gets too high relative to the screen sampling rate. Very, very useful here. So here's, for example, a very simple small shader. Just as an example, it's the so-called cool warm shader from was a SIGGRAPH paper many years ago from Gooch. So it's actually 2 students. Both was a pair. So here you have a light position, that's all the uniform parameters that you specify for the shader. So it's a fragment shader that we're talking, sorry, a vertex shader. So for the vertex shader, we specify where's the light source. So we assume there's only one. You have matrices for the model view transformation. For the model view, including the projection to camera coordinates. Sorry, to screen coordinates here. Canonical view frustum coordinates. And we have a separate matrix for normal vectors, right? Then you get the position and the normal. These are the attributes you get from the draw call. So you need to specify not just the position, but also a normal. And then you output to the fragment shader a normal, the vector to the light source, and the vector to the camera. And the idea is clear. We want to do the lighting computation then in the fragment shader. And so the first thing we are doing here in this vertex shader is we're computing the GL position. Remember, that was the output from the vertex shader. And we do this by applying the model view projection matrix to our position of the vertex. And we're also computing it, we're not projecting it, but we want to only compute its position in world space or in view space, camera space, right? So we compute this vert variable here by not project model view, but not adding the projection to it. And then we also compute the normal vector, but because the normal vector, again, we don't transform that with the same matrix, but with a different transformation matrix. That's typically the transpose of the inverse, as you know, as we've discussed. So here we transform the normal by its matrix, which we assume is that transpose of the inverse. And then we compute the light vector by simply write the difference between the position of the light source and the position of the vertex in camera coordinates. And the view vector is, obviously, this is the position of the vertex because the camera is at, right in those camera coordinates, obviously the camera is at the origin. So, and then with those, so right, and this fragment shader now outputs normal light vec and view vec. And so we have the fragment shader as the second one that obviously now takes exactly those three values as input. So they're specified here, they're as in with the same types. And we also here have and here you see that right here we have a uniform block. So not just this individual variable, but an entire block here, like a structure. Where we have the ambient, the diffuse, and the specular coefficient. We have here the ambient light color, the specular color, and then the warm and cool colors. That's the idea of this shader, that you actually interpolate colors between the cool color here, which is this purple color here in the back, and the orange color, which is here in front. And on top of that, you have white highlights for the specular component, right? And so, and the output of this shader is the color of the fragment, right? So first of all, we normalize all these vectors. We compute the half angle, right, between the light vector and the view vector. That's like the Lin-Fong model. We clamp that. We clamp the dot product of the half angle vector of the half vector with the normal vector. We clamp that to 0, 1. Then we compute the power. So this is the exponent specular exponent here, the dot product to power 64. So fairly narrow highlight. And then we compute that mixture between the warm and the cool color by simply taking the dot product here, which is between 0 and 1, and mapping it to the range 0 to 1 by multiplying it 1/2 and adding 1/2 to it, right? And so instead of the diffuse color, you interpolate between those two, And then you do the standard Phong model here, right? You have the ambient coefficient times the ambient light here. You have this diffuse coefficient, which in this case is just a single factor. And it takes the color from the Gooch color that we just computed, and you add the specular component to it, right? Which is the specular color, the color of the specular highlight, times the specular component times the spec color that we just, the power here, that the normal vector to some cosine to some power. And then you pack this all into a fragment color, set the W component to 1 and return this. And you get such a nice picture like here on the right. Actually, it's not exactly that picture because the one thing that is missing is, and if you've been careful, you might have seen this, that here in this case, the silhouette of the objects are also drawn in black with black outlines. So you kind of very clearly see this, for example, here, where, right, you have the lower part of the spring here, you have the outline, which then vanishes here because it's no longer an outline. There are special shaders for doing this kind of operation, so this is not included here, but it makes it even nicer. So you can find these kind of outline silhouette shaders. There's many examples, and there's entire collections of shaders in various shading languages that you can look up. We don't have time for that here. So in the following, we go through a simple OpenGL program just to give you a feel of how that all fits together. The details are here on this. You can look this up. I hope this is still up. I didn't check this year, but I hope it is. So in particular, we will use the GLUT library, GLUT, or GL utility library, for doing this. This is not the most modern way of doing this, but it's quite easy and convenient to do that. So here's our main program. We include a couple of headers. This is our main program. We get the arguments from the command line. We give those arguments to the GLUT init function, which actually picks out any standard command line arguments that GLUT understands. So for instance, you can specify the window size and things, the window position, and it grabs them from the command line and actually removes them from the command line. So you don't have to deal with those. Then here we're saying, okay, we want to render, this is where you specify what kind of window you want, right? So here we want an RGB color part in the window, but we also want a depth buffer, and we do want double buffering. Then here we say, well, even though we can specify the window size in the arguments, here we just overwrite this and says, okay, we want a window of 400 by 300 pixels. We give it a title. We give the window a title, and then we set up two callback functions for GLUT. And the one says, whenever GLUT wants to render something, please call this function render. And whenever there's nothing to do, so essentially once everything has been rendered, please call that update function, so the idle function. So this is a typical way how graphics interactive applications, or in particular, or simulations operate. So essentially you render a frame, then you look up how much time is this taking. So what is the current time? How much time happened between the last time I rendered and now? And you take that time to advance your animation, right? So if you have an object that moves at, I don't know, 2 meters per second, right? And then the rendering between two frames takes, I don't know, 15 milliseconds. Then you compute how much should that object have been moved in that time frame. And so you change its transformation matrix to be at that location where it would be now if given whatever velocity it, for example, had in your application. So once we're done with everything, we the next thing we're doing is we initialize the extension Wrangler library. I didn't talk too much about that, but OpenGL allows vendors to add extensions to OpenGL and so there might be certain functionalities in OpenGL. So there's certain base functionality that's always there given the current version of OpenGL of the driver, of the version that the driver implements. But on top of that, there can be extensions that are there or might not be there. And dealing with them is a little bit tricky. And so the extension Wrangler library, which is open source, allows to do things much simpler. In this case here, we just use it just to make sure that we get the right version of OpenGL, at least 2.0. So it also runs. And then you have the main loop, which essentially Glsl takes over now and just waits for things to happen or time to pass, and it will call back into the application, specifically these two functions, update and render. Right. So for update, we ask Glsl of how much time has elapsed since the last time we called, we asked for the time. And then we could animate the scene here, right? So for simplicity, we're not doing much here, except that, of course, after we've changed the scene, we now have to tell Glsl, please render the updated scene, right? And we do that by telling Glsl that please start a redisplay, which essentially simply means Glsl, please eventually call the function Glsl that we set up here with Glsl display func. So essentially, it will call the render function, right, at some convenient point for Glsl. So what are we doing here in this render function? So this is not the most efficient way. This is more for demonstration purposes here. We enable depth testing. We enable backface culling. We set the clear color, and we do clear the color buffer and the depth buffer. Okay. Then we would do the real rendering here. And when we're done, remember that we're doing double buffering. When we're done with rendering, then we have to switch the buffer that so far has been displayed with the new buffer that we've just rendered into. And so the next time we render, we then again render into the other buffer, and the one that we currently created will now be displayed. So this is the general structure. Let's set up again a simple OpenGL, the shaders that we will be using. Just another example. Of course, we need the source code. We specify which version of Glsl we'll be using here, which just tells the compiler to adapt to that. Again, we have here two matrices, the model view matrix and the projection matrix. We are getting from these attributes here is essentially the input that we had before, the position normal, we get texture coordinates, we get a shininess value and a specular value. So there's quite a number of attributes that we're expecting. And then we're outputting the fragment position, the fragment normal, texture coordinates, shininess, and specular. So we interpolate all of those values and then provide them. So we read them in the vertex color and then make them essentially just pass them through to the fragment shader. So here we, of course, we take the position, do our model view. So we have the eye position here. We take the eye position and multiply it by the projection matrix. So it's similar to this last example where we had a combined matrix for that already. The fragment position is now just the XYZ component of that. The normal vector, here we're apparently are assuming that our model view matrix is an orthonormal matrix, because otherwise we would have to have an extra matrix just for normals. Or we would have to compute the transform of the inverse, but that would be stupid because we would do that per vertex, right? This vertex shader, of course, gets called for each vertex. So you definitely want to compute that matrix outside and pass it in to the vertex shader. But so here we apparently assume that our model view matrix is orthonormal, in which case the inverse is equal to the transpose, and so the transpose of the inverse is really the matrix itself. We all discussed that. And we simply pass texture coordinates, shininess, and specular through to the fragment shader. Nothing really happens here. This is not actually using any computation, right? This is just setting up, passing things to. So here on the fragment shader, again, we actually get the same matrices here as uniform variables. We get the sampler, so we get a texture, and we get these varying components as input, which is essentially the same thing as here on the left. We're computing. We have the light direction here as a as constants, right? So this again will not be computed. The compiler will pre-compute this, and there will be nothing will be done for that. And then we compute here the light direction. So we do the lighting computation now on a per vertex, on a per fragment part. So we compute here we transform them into model view coordinates, the light direction into model view coordinates. Normalize the vectors, compute the reflection of the lighting direction, right? Then we look up the diffuse color in a texture with this texture 2D call, where we use the texture coordinates that have been passed in from and interpolated across the triangle, right? So this is the part that maybe I should mention. So here in the in the vertex shader, right? The texture coordinates on it are passed in as an attribute of the vertex, right? So we output them to the fragment shader, which now means these variant parameters here are interpolated. And so here in the fragment shader, we receive the interpolated values, right? And so we get the interpolated texture coordinates, and we look up the texture color and the color from the texture here. The diffuse factor is whatever we're doing here. So this is essentially a little bit of lighting computation, and then at the end we're having here an ambient factor and a specular factor, and compute the output color. Okay, so however, where we would have to do the rendering in the application, so back at the application code now, this was shader code, which, right, you write separately. So of course, in the application, before you use the shader, you have to compile this. We talked about this. The way we do this here, so here's a function that calls make shader. It says what type of shader and the file name for the source code. Of course, there's different ways to do this here. Essentially what we're doing, right, you saw that we create a shader. So we, right, an ID, we give OpenGL the source code. We compile the shader, then we read back the status, the compile status, so whether that worked. If not, then we delete the shader and stop. And if all worked, then we return the shader ID that we queried here. And then there's a function to actually create a shader program here, where we pass in the vertex shader and the fragment shader. We don't care about the other types here. And again, this is pretty much of what I already talked about. We create a program, we attach both of those shaders to the program, we link the program. Again, we ask for the link status in this case, whether this is all fine. Otherwise, we simply return 0, which says, okay, it hasn't worked, error condition. Otherwise, we return the ID of the program. Also, of course, we need to find out where, remember, we need to find out where these shader variables, how can we access them from our application? And so, oops, sorry. We ask OpenGL, what is the uniform location, given the program that we've just created here, right? Which, so this is not a full source code here. So here's just somewhere in your program, right? Once you have called this make program, you now have an ID for the program. You can now ask this program for where right, is the uniform variable called texture, and where is the attribute slot for position, for the variable position that we had in the shader, and so on. Of course, we also need to define a texture, right? Remember, we just used the texture. So we read, somehow we read in whatever format, we read the pixels from the file name. And we return also here from that read operation, we return the width and the height of the texture. Then we generate a texture ID. We bind this texture to a 2D. So essentially saying we want this to be a 2D texture. Then you set some texture parameters. So the min filter, linear interpolation, the mag filter also to be linear. We wanted to warp, to clamp to 0. Oops, sorry. We want to clamp in S&T, the texture coordinate, so in horizontally and vertically to clamp it to the, so we want to wrap around in S&T and clamp to the edge. And then here, and then we define the texture data. We pass the texture data to OpenGL. We say here, okay, it's for the 2D texture where we bound, this is where we bound the texture. Level of detail 0, so this is the normal texture data, so no bitmaps or anything. We tell it that this is 8-bit RGB values. This is how we want to store things in the GPU. We give it the width and the height, and border width always has to be 0. And then we tell it how the memory of our pixels are organized. So this is in the 3 values, and it's in the inverse order, not RGB, but VGR. And there's an unsigned byte value for each of the RGB values. So it's between 0 and 255. And then there's an array. This is what we read back from the image file, right? And at the end, we free the data that we've read in, because OpenGL now has the texture and we can discard the pixels in the application. Of course, we need somehow to store the geometry. So we actually, the way we do that is we, for each vertex, we store 4 floating point values for the position, for the normal, 2 texture coordinates, the shiny, and a specular color. The color here with 3 bytes, all the others with floating point values. The first thing we need to do is to actually, we want all of this data to be in a buffer on the GPU, right? So first of all, we allocate data here for storing all of the geometry here. This is for the vertices here and for the connection information, so the index information. And then we allocate 2 buffers. One is for the vertex, the array of vertices. And the second one is for the buffer with the index value. So which vertex is being connected in which order to form triangles. Then we bind the vertex buffer that we just created here to the array buffer. And then we send those the data. So we've allocated the data up here. Of course, we also need to fill it with real data. So I've left this out here. So here we're just transforming whatever is now here in this memory. We send this to the GPU here. So it's the number of vertices times the size of this structure here. And we tell OpenGL, so vertex data is what we allocated here. This is where the data is in application memory. And we tell, this is a flag at the very end of this buffer data call, which tells OpenGL, hey, we're going to use this data here for drawing. So OpenGL can expect us to use this for every frame. And we do the same thing for the index buffer, right? We bind this, first we bind this here, then we send the certain amount of data, and we, why is this static draw here? Not really sure why this is stream draw. So this is taken from some examples on the internet. I guess the idea is that the connection between the vertices remains the same. So you say, I'll use this for drawing, but this will stay static. I will not change this. This is stream draw here for the vertices, because in the animation, you might actually change the position. So OpenGL should expect you to change the content of the first array, but not of the second. And so it might optimize this internally in some way. So when you actually want to do the rendering operations in OpenGL, right? So this render function, right, you saw the beginning of that code. And so here now, in addition to that, first of all, we'll say, oh, we will use that program that we created. Or remember, there was this make program, or whatever the name of that function was. Here we're saying, okay, now start using this program. Actually, since we only have a single program, we can, we don't have to do this every time, but so this is more for deductive purposes. If you want to optimize things a little bit, then you should probably just set this once in the very beginning, and just OpenGL will keep using it until you change it. We will activate the texture, again, something that you could do only once. We don't, in this case here, you don't have to do this for every frame. We activate the texture 0, we bind our texture to that value, and we tell the current program that for slot, for the so this is the slot for this is the slot in the uniform variables for the variable called texture in the shader, right? And here, since we only have a single shader, we simply pass 0, because that is the right. Actually, that should actually be GL texture 0, but it's the same thing. Turns out this is the same thing. It's not the nice. I should probably change this. Okay, so but then so we enable texture, or we bound the texture to the shader, so the shader can use the texture now. Then we bind the array buffer, right? And then, and this is a little bit more complex, we do a GL vertex array attrib pointer. So essentially, we're now telling OpenGL for each of the slot of the attributes, right? So here's for the attribute where we store the position, we tell it that there will be 3 values, right? Because X, Y, Z, that it will be a floating point value. I forgot what that false is here. This is the step size between consecutive entries in the array. Of course, because the data is stored in these structures, the step size from one position to the next one is just the size of these structures. And it starts at the location, so that's the offset of the variable position in that structure, right? So essentially, we're saying wherever the data, the RGB data is, the position data is in the structure, whatever that distance from the beginning of the structure is, that is the offset that OpenGL should start reading from. And then the next XYZ coordinate is the size of the structure later, and so on. So essentially you have the vertex position, the color and the texture coordinate, and so on. You have this all interleaved in one single array. And we do the same thing for the normal information, for the texture information, for the shininess and the specular information. Then we bind the element buffer to the GL element array buffer. So we now have all the attributes set up. We have the index information set up. So now we can actually draw. right? We call GL draw elements. We say these are triangles, so they're individual triangles, each one with its own vertex information. We say how many elements there are, and we say that the index information is unsigned short. We pass 0 for the data because that simply remember that this means if we have bound a buffer, then it will start using from the buffer, and the 0 here simply means start at the beginning of the buffer. All the other offsets are already in the attrib pointer. Yeah, and with that we're done. So sorry, I took a little bit longer now, but I wanted to finish this. So essentially now we've gone through the API of OpenGL. We've looked into shading languages today, and we've all put this together in at least a short OpenGL program where you had the shader, you had the main program, you had the drawing code and all the setup code. Of course, this is not complete. If you really want to play around with these kind of things, there's plenty of code on the internet that you can start looking at. Yes, so this is essentially our overview of OpenGL, and we'll see if we can add, yeah, and this gets you started to also to use OpenGL. And we'll, I believe we also do an exercise with a little bit of OpenGL program. With that, that's all of it for today. Sorry for running a little bit over, but I think it makes sense to finish this today, so we can start fresh with a new topic on next week on Monday. So since it's a little bit late and there are typically no questions, actually I'll end it right here. If there's any remaining questions, we can please remember them until Monday, and then we'll do them on Monday. With that, that's it for today. Thank you very much, and see you on Monday then. Bye-bye.